she will tell you about her research, which is also food-based.
Give me 1 second. I'm just going to get to my presentation. Here we go. Okay, yeah, so like Dr. Asano said, my mom named me Rita Dill. The title of my research is HPTLC, and that's High Performance Thin Layer Chromatography Method Development for Classifying 23 Different Dried Bean Cultivars. As Dr. Asano stated, she works in collaboration with Dr. Devin and Luthria from the USDA, and she is a plant scientist who leads me in the research. So, the focus of my research is beans. Beans are important. They have significance in America, to the extent that we're the 6th largest producer of beans, and 20% of what we're producing here is actually exported. That's kind of significant, right? Because last time I checked, berries tend to be imported, so it's pretty cool when we have something that we're sending out to other countries. Along with that, we consume a lot of beans. I don't know if anyone else noticed this, but I think beans was on the menu today. Maybe that was planned. However, beans are significant. We are eating them. But regardless of that, statistically speaking, 14% of Americans consume beans daily, according to research. If we know that people are consuming beans, we should also know that they're consuming them for specific reasons, one of which is for their phytochemical content. Phytochemicals are naturally produced chemicals from the plant. They're nothing to be scared of. In fact, Dr. Asano specializes with phytochemicals. It's essentially the vitamin, the nutrients coming from the plant. It's naturally produced. We know phytochemicals to be things such as ascorbic acid, also known as vitamin C, or beta-carotene, which is a form of vitamin A. Beans are important, and so is their phytochemical content. However, there are certain reasons that contribute to who is going to be consuming beans. And one of those reasons, or factors, happens to be income levels. If you are an individual of a lower income level, research indicates that you're more likely to consume beans than those of higher income levels. And if we know that people who are consuming beans and they're of a lower income level, that tells us they're shopping on a budget. They have X amount of dollars to spend every month. And we should take advantage of that and cater to that. If we know that they're shopping on a budget, let us be sensible in the choices that we make with our beans. I don't want to buy fava beans, which are actually very expensive. If I could buy lima beans and they have the same phytochemical content, it doesn't make sense to me. We must optimize our choices better. We must enable the consumers, the dietitians, the nutritionists, the agriculturalists to know what is similar in the beans in terms of phytochemical content. To be specific, polar phytochemicals, semipolar phytochemicals, and non-polar phytochemicals. These different types of phytochemicals just represent different types of nutrients that we can look at. And my research will clarify which beans fall into what categories, and are they the same, are they not the same? This is significant research, guys. Don't sleep on my research. It will have an impact. So, however, in order to come across all these things, to verify my hypothesis, which is that, yes, I can place these beans into certain classes, and yes, I can do it by extracting out the beans and using this technology that Dr. Asano has in her lab, the high-performance thin-layer chromatography and different softwares. In order to do that, I have to start somewhere, and I start somewhere with sample preparation. I'm given beans by the USDA, Dr. Asano's collaborator to be exact. He has a contact that provided us with these dried beans. It's 23 samples. If you look on the slide, it shows this chart that I made, and it says like number 1, number 2, and it's the pink bean, and the speckled butter, and the cranberry. Those are the different types of beans that I used. We selected those beans out of a few hundred. They were chosen because they're the ones that the everyday consumer is going to come across when they go to the grocery store. When I go to Giant Food, I can buy a garbanzo bean, and it's easy. I don't have to search very hard for it. That is why we chose those beans. That's why it's exactly 23. We picked the ones that are going to be most impactful because research should impact the consumer. So I'd like to move over here though and point out that they were actually air dried, yes, but they're also ground. So that just means we put them in a coffee grinder, and it allows us to use our samples in a more efficient manner. After we had those samples ground through the coffee grinder, I added some chemicals to it that corresponded to their polarity. So I added hexane for my polar phytochemicals that I'm interested in looking at, and then to the samples that were semipolar, I added ethyl acetate, and then to the to the phytochemicals that were polar, I added a solvent system of methanol and water in a 1-to-1 ratio. Extraction is done in the lab using an ultrasonicator. Dr. Asano actually has an ultrasonicator, and we can see it in figure 1 right there. That's her ultrasonicator with a few samples in it. The ultrasonicator uses sound energy to increase the interaction between the solute, which in this case are my bean samples, and the solvent, which is the chemicals that I just talked about that I add to these ground up samples. Post that, I come up, after a few other steps of centrifugation, I come to this, which is a supernatant sample. So as you can see, it's just about a milliliter or two, so it's a couple teardrops. And that's just the sample that I have afterwards. It's in a liquid format. Once I have it in a liquid format, I'm able to follow up with an HPTLC, which as I said is high-performance thin-layer chromatography analysis. HPTLC is derived from TLC, but it's a bit more advanced. It's a bit more quantitative, if you will. And for those who don't understand, qualitative is saying, here's something, but quantitative is saying, here's something, and here's some extra information about it, and that's what HPTLC lets us do. Because of the sophistication of the machine, we are able to accomplish these things. So here, we will look at figure 3, and this is step 1 to doing HPTLC. We start out with a silica gel plate. Ours are 20 centimeter by 10 centimeter. This is a very good image replicating that. We use a piece of machinery, and to be clear, all of this machinery is in Dr. Asano's lab. We use this machinery, which is the Linomat 5. It's produced by ChemAg. It's the company that makes it. The Linomat 5 allows us to be able to control how much of the sample is placed onto these silica gel plates. Now, in commonplace TLC, you would not necessarily be able to control it down to the decimal point. But with HPTLC, you can. It's automated. It's a machine doing it for me. And that's where we get this quantitative side of it. It's hard to do quantitative when you do regular TLC. With this HPTLC, you can do quantitative. Oops, my bad. Hold on. Okay, sorry about that. Okay, excellent. So, following from the Linomat 5, we proceed with using mobile phase chambers. There's some significance here because if you noticed in a previous slide, I had discussed that we're doing method development. So there is not a method currently that discusses how to look at these different beans or how to look at this many samples, specifically beans, and be able to look at their polarities with HPTLC. But this research allows me to do that. This research has accomplished that goal, and now we have literature. We have something that shows how to make these HPTLC plates happen. And that is significant. That is publishable work. There's potential here. From there, we move on to placing our plates through sulfuric acid, which just allows us to see the plate better when we take the image of it in step 3 with a TLC visualizer. It simply allows us to get images that look like this. This is a beautiful picture of the plate. You'll see over here that there are some bands further down. Those bands are those controlled amounts of sample that I was able to place onto the plate. I can control it down to the microliters. I can tell it how much to put on the plate. And from there, when the plate was placed into the mobile phase chamber, these bands actually produced phytochemicals that came up. You'll see all these different little bands right here. This is this initial spot separating out into different phytochemicals. It tells us there are this many phytochemicals in here, and we can see it under this wavelength, which to be precise is 366 nanometers. Now, we'll move forward, and these are the other plates matching with the type of mobile phase that we selected. After a lot of trial and error, we did invest a great deal of time into this research. Additionally, once you have those HPTLC plates, you're able to do manipulation with the software that we have, which is Vision Cats. And Vision Cats allows us to get chromatograms such as these. These chromatograms show us just a different way of looking at the data that we saw on those plates. The peaks are representative of the bands, or essentially the phytochemicals that we're seeing in these plates. And you'll see that that's kind of represented in a Y format, but then there's an X-axis. And the X-axis represents the RF value, so the way that the solvent is moving. And from those plates, you're able to generate X and Y data formats. So the X and Y data is just characteristic of what was happening on that particular chromatogram. It corresponds to the chromatogram, and it is significant because once we receive those X and Y data points from our VisionCat software, we're able to follow up with a third-party analysis of that data. We use a company called SoloSoft, which is produced by Eigenvector. Eigenvector allows us to have different dendrograms, or things that are hierarchical content analysis pieces of data, and they let us be able to look at the classes in a particular way. So you'll notice at the end of these heading, it says like figure 5 has these many phytochemical classes. It's just talking about our end results, but pay no attention to what's happening out here. Look at these colors. The different colors represent the different classes. So from those X and Y data points, which were characteristic of each individual band that we had, they were able to tell us that this can be placed into one class. So baby lima beans and butter and black and white and navy beans were placed into one class. We have 3 different pieces of data which show this, and they correspond to the 3 different types of polarities we have. This research is significant. It will need to be followed up with HPTLC mass spec for analysis to further confirm our findings, because you cannot just say, okay, one and done. No, there must be a second confirmation. There must be something else to validate our findings, and we will follow up with that. In addition, we will follow up with better optimizing mobile phases if possible. And aside from that, those are our plans for the future of the research. Finally, I come to my acknowledgements, and I thank everyone for their patience as I've given my presentation. I understand I went a bit over time, but I feel this slide is very significant and important. I would like to thank Dr. Asano for her patience with me and for being my mentor. She has become such a wonderful person in my life, and I am truly grateful for the relationship I have with her. And I'm grateful for Surrey and the NSF and the other people that were involved in making this possible. I am so grateful. I cannot begin to express the gratitude that I have. I did not think 2 years ago that I would be doing this, so I am eternally grateful. But beyond all, I thank my Creator for bringing these people into my life, because it is not by any coincidence that I am here today. I thank God for bringing Dr. Asano to me and for making these things happen in my life. I am truly grateful. Dr. Ude is coming near me, so I know that it's my cue to put the mic down. Thank you.
Thank you, Rita. Thank you so much. Question time. Rita, come. We have a lot of questions, I'm sure. Questions?
Right, so that is a good question. And so if I had the pointer, I would go back to the chromatogram slide. And we see that the y-axis, some of them peak up, and then some of them don't really peak up. So that's indicating what is happening with those big bands. It's indicating the intensity of it. So it's telling me like one is not as intense as the other. But I have been informed that it is okay for one to be a little bit more intense than the other, because that's indicating that maybe this particular phytochemical is not necessarily present in the other. And that's perfectly fine, because we have different bean samples. So we wouldn't want the bean samples to be identical, then we should all eat the same beans. I don't know if that answered your question effectively though.
What do use sulfuric acid, and then also
So first question. So yeah, so sulfuric acid. So with HPTLC, there's a lot of literature that shows us that when we dip it in sulfuric acid, it's essentially, I hate to use the word charring, but that's a pretty good word for it. It's essentially charring the plate, which then illuminates it. If we went back to the slide, you'd notice that the upper portion of the picture of the plate is black. However, that's still part of the plate. That's just the part that didn't get derivatized, or didn't get dipped in the 10% sulfuric acid. So it's not to say the bands aren't already there, it's just to say that it illuminates them more. It's just another method, like doing the iodine chamber to see it. It's just another way of looking at it. Some are more reactive to that, so that we can see it in a visible manner. As for the other one with the cancer cells, it'd be really nice.
Some phenotype to say that when I do my HPTLC, this band is more prevalent in beings that produce cholesterol, so maybe this is the phytochemical that we need to isolate as a new cholesterol drug, something like that. Thinking about that?
Future research.
Future.
Future.
That's another project. Yes.
Thank you, Dr. Smith. Any other questions?
Chemistry with biology.